General Chemistry students. This is week 10 of General Chemistry 2, and this week we're going to be looking at rates and chemical kinetics. So for this first video, some things that we're going to be able to do at the end of this video are to describe the concept of a reaction rate, define what a reaction rate is, and then also we'll be able to compare and contrast rates based on concentrations over time, right? Some things that you may have to do on your own is learning how to graph that data and determining averages. All right, so let's talk about reaction rates. So I want to bring up this idea of the ectotherm. So ectotherms are cold-blooded creatures. You can think of the lizard family here. And they're cold-blooded, so what that means is that their internal temperature matches the outside environment. So one thing that we're going to learn later on is that in chemical kinetics, the temperature really affects the rates of reaction. It can really slow down a reaction. So when a lizard's body temperature drops, these chemical reactions in the lizard's body slows down. And so this is actually a survival mechanism for lizards because they can survive pretty cold temperatures because they're able to essentially control the chemical kinetics or the metabolism in their body. So this is how ectotherms or other cold-blooded animals deal with their environment, okay? And so all of this has to do with this idea of chemical kinetics. So we're going to be looking at the factors that control rates of reactions. And in this case, with our lovely ectotherms, it's temperature. All right, so what is chemical kinetics? Chemical kinetics is really the speed of a reaction. We're going to be using the term reaction rate a lot in this unit, where the rate of reaction is the measure of how fast you make products or how fast you use up reactants. And so really importantly in chemical kinetics, it's really important to be able to control the rates of reactions, and you can do this a number of ways. So we talked about the lovely lizard where he's able to slow down chemical reactions with temperature because the temperature drops. So temperature is one way in which we can control chemical kinetics. Another way we can control chemical kinetics is by adding a catalyst. So a catalyst will serve to speed up a reaction. So there's lots of ways that we can do this, that we can control rates of reactions. All right, so what is a rate? So rate really is a generic term for the quantity of change in a given period of time. So you can think of this as how fast you drive your car. So if you, normally when you're, on your speedometer, it says miles per hour. Well, that is a rate, okay? So how many miles can you go in a given period of time? In this case, an hour. And so speed is one of the forms of rate. All right, but in this class, in chemistry, we're going to be talking about reaction rates. So when we talk about reaction rates, the quantity that we're going to use is concentration. And the time can vary from seconds to minutes to hours, even days, but really, we want to make sure that we're using concentration as our, to determine our reaction rates. So for reactants, here, the change of concentration is going to be negative because if you think about it, you have reactants that go to products. The reactants should be going away and the product should be forming. So we'd put a negative sign on the reactants and a positive sign on the products. All right, so let's look at this reaction. We have two of them. Here we have reaction A plus B goes to C, and we have X plus Y goes to Z, and you can see that their forms as C grows in, you can see the little capsule, that little purple capsule, and as Z grows in, you can see the green capsule. And if we just look at these molecules, so we have in the first, that's when t equals 0. Okay, so t equals 0. We should have, in this case, we have the same number of reactants to each other. So X, Y, and A and B are the same. Okay, and so on one side it says, well, this reaction is fast, and on the other side it says, well, this reaction is slow. How do we determine that? Well, the reactants should go away and the products should form in. So if we look at, okay, so t equals 16. So by our count, we're at 16. So here we have 4 less of A and 4 less of B to form 4 of C. And on the right, we have 7 of X, 7 of Y, and we've only formed 1. So when we say one reaction is faster than the other, what we mean is, well, the reactants are going away at a faster rate, and the products are forming at a faster rate. All right, so let's look at this now at t equals 17. Or sorry, t equals 16, and compare it to t equals 32. So now we're going to double in time here. And so our fast rate has reduced our reactants to 2 and 2, making our product 6. And our slower rate has reduced our reactants to 6 and 6 with our products 2. And you can see that at t equals 32, we have 3 times more of our product on the fast side than we do on our slow side. And here I'm just counting molecules as all I'm doing. All right, and we can extend that out further to yet another 16 interval. And in this case, we use up all our reactants on the fast side to form all products, but we're still lagging behind on the slow, where we now have a mixture, almost equal mixture of reactants and products. Okay, so let's look at this in terms of data. So we have this hypothetical reaction where red goes to blue. Okay, when we start at 0, we have all reactants and no products. So we have 100 molecules total, all right? And so we have 0, molecules of blue, because that's the product. At 0, we should have no product. All right, and so we're assuming that 1 molecule of red turns to 1 molecule of blue. That means that we'll always have a total of 100 molecules because of the law of conservation of mass. Okay, so we can't have more than we started with or less than we started with. It has to go somewhere. So here we'll have 100 molecules of red that go to 100 molecules of blue eventually. All right, so the rate of reaction is going to be measured either by the loss of red or the gain of blue over time. Okay, so let's plot this out. So what you see in red are the number of molecules of red over time. So of course I start with 100 molecules of red, and then at 50 seconds I'm down to only 18 molecules of red. Okay, so the opposite is true of blue, where I start with 0 molecules of blue, and then over time I have 82 molecules of blue. And notice that at any given time, the sum of the two has to equal 100. That's because of the law of conservation of mass. We have to have what we start with. Okay, so at the end, at 50 seconds, we have 18 molecules of red and 82 molecules of blue. Well, that does add to 100. Okay, and we can look at this a different way. So we can look at this in terms of rate of formation of blue. And so if we do that, find the rate of formation of blue, what we see here is that over time, that rate of the reaction starts to decrease. Okay, so initially it's pretty fast, and then over time it gets slower and slower. And so the reason that is, the reason the reaction rates change over time really is because concentrations are changing over time. And concentrations really lead to how fast a reaction is going to go. And we're going to see that when we start looking at rate laws. So over time, the rate of reaction is going to slow down. And that's because the concentration of those reactants is going to decrease, so not as much to react with. And then we also have to think about it that at some point the reaction's got to stop. All right, and this can happen by two ways. Either the reactants run out, right, and there's nothing more to react, or the system has reached an equilibrium. And what I mean by equilibrium here is that the concentration of reactants and the concentration of products are not changing, right? So they're in equilibrium. So if the concentrations don't change, the system has reached an equilibrium. And what that means then is that you have some concentration of reactants and some concentrations of products that are no longer reacting with each other. All right, so that's it for video 1.